Welcome into lecture number 3 of Calculus 3. This lecture is going to be on the geometry of space curves. So let's first start by talking about arc length. For the entirety of this lecture, we are going to talk about geometric properties of the space curves themselves. So let's say we have a space curve here floating around in space, but let's also assume that this space curve is given as the graph of some vector function, or we could say that the vector function parametrizes the space curve. We're going to set some criteria on this vector function before we get started. So let's suppose that R is a smooth vector function that parametrizes the space curve. That just means that the space curve is its graph, right? And we're going to remember what smooth means here in a second. But let me finish writing. So it's going to parametrize our space curve C. And recall that smooth in our Calc 3 context means two things. It means that R dot exists, so the derivative, dr dt exists, and R dot is not equal to 0 on the domain, right? So the length of R dot is never zero. So if it's a length, I don't need the hat, right? But if the length of R dot is not 0, that means that the vector, the derivative itself, the vector is not the 0 vector. Okay, well, here's the problem that we want to try to solve to start out with. Let's suppose that we have 2 points on our space curve, say here and here, and we can assume, because we made this assumption about the vector function parametrizing the curve, that these 2 points correspond to inputs or outputs from the vector function. So R of A, the point capital A is going to correspond to R of little a, and the point capital B on the space curve is going to correspond to R of lowercase b. So the lowercase a and the lowercase b here are values of t, right? If we think of the space curve as the path of a particle, then those correspond to the times, right? The inputs, the t's, time. So R of t. What we would like to do now, though, is try to find a way to measure the length of the curve, the distance traveled by that particle between those points, capital A and capital B. So we're going to try to relate distance to time. The length of this curve is a property of the curve itself, right? The length of the curve segment from A to B is a property of the curve C itself. But to compute it, we're going to use this parametrization R, which takes into account this time and therefore the speed at which the particle will travel this curve. But obviously we want the length of the curve to be the same no matter what the speed is of the particle that's traveling along the curve. So that's a little bit of the subtleties that we're going to encounter as we move forward here. But let's start this process by just thinking back to Calc 2 and how we would have done this in, say, the Calc 2 sense. The Calc 2 idea would be to partition. So partition our space curve into subcurves, subpoints, right? So we'll find some partition of points where the first partition point, P0, is just going to be A. And then from there, we'll chop up our curve into a bunch of points, right? So P1, P2, etc. But a finite number of points. So P0, P1, P2, etc. And our last one, Pn we'll call it, that'll be equal to B. So that's where we end. All right, and these points will correspond to t values, right? T values between A and B. So the other side of this, if we go, so that right now what I've written here in green is in reference to the points on the curve itself. But remember, we've got this vector function which parametrizes the curve. And so these are going to also correspond to the following. We're going to have a kind of a partition of the t values as well, right? So we'll have our partition A equals T0, and then the partition of the t values, these have to be ordered, right? So then we'll have T1 less than T2 less than etc. all the way up to Tn, which that'll correspond to our lowercase b. So this partition comes in two forms. It comes in the points that we've used to chop up the curve and the t values that we have to chop up our domain of our vector function with. All right? The idea is once we have the partition, we're going to connect with line segments, right? Line segments here. And then we can use the line segments to approximate the length of the curve. So if we call the length of the curve L, then L is going to be approximately equal to the sum of the lengths of these line segments, right? And so I'm going to use actually vector notation to represent the lengths of these line segments because, for example, this segment right here, if we just write it in like Euclidean geometric notation, this would be AP1. But if we just put a little arrow here, right, then that becomes a vector, and its length is what we're looking at, right? So the length of our curve is then approximately equal to the sum, as k goes from 1 to n, of the lengths of these vectors. So the lengths of pk minus 1, pk as vectors. And that's it. So, but that's not the answer, right? But that's just how we write down this approximation. L is approximately equal to this. Now, how are we going to get an exact answer? Well, again, think back to how we did this in Calc 2. You take more and more partition points, which means a larger partition of your t, and a larger meaning more points, a refinement it's called, right? A refined partition of the t values, and then you take the limit as the number of partition points approaches infinity, right? And you end up with what's called a Riemann sum, and then you can write down an integral. So the actual arc length is then going to be equal to the limit of this exact approximation as n approaches infinity, right? So k goes from 1 to n of this same deal, right? Pk minus 1, pk, these lengths. So geometrically, that's exactly what we want to compute. Now the question becomes, how are we going to compute that in terms of the curve itself? And obviously the vector function is going to be one of our tools. So how are we going to get this in terms of the vector function r? So let's zoom in on just this one instance and see if we can make sense of this. I'm going to do this two ways, all right? Well, I'll do it one way, and then we'll notice how r comes into play, all right? But here I'm going to, like I said, try to zoom in on this picture and try to keep it similarly oriented to what we have here. So here's our point A, which corresponds to P0. And by the way, it doesn't have to be this. Probably what I should do is just zoom in on a generic portion of the curve. So let's call this one PK, and then I'm going to erase this and rename this one as PK minus 1. All right, because this is what we're going to do here is going to be true for any point on the curve. Now, our vector that we've used, so we've connected these, right, with what looks like a secant vector, and it shouldn't be crossing the curve there, but my drawing's not great. This vector, though, is PK minus 1, PK, in this direction, right? Now, as we take the limit, right, so as k approaches infinity, then this little delta, the little change here, this point, right, as the change gets smaller, as we get more and more points, these points are going to move closer and closer together. But before we look at it that way, let's just try to compute this here. So I'm going to call this the term that shows up here, right? This is going to be the length of this pk minus 1 pk vector. And the way that we can compute this is just by kind of sketching some little changes. So this will be like our delta x, or change in the x direction. And then we'll come out to here. Maybe this one we have to go this way. So that's going to be our delta y. And then this should have been straight up and down, so I'll fix this. But this one then will be our delta z, right? And this just obeys our three-dimensional Pythagorean theorem, right, at this point. So we can then write that this is going to be equal to, so this squared is equal to the sum of these squared, right? So delta x squared plus delta y squared plus delta z squared by the three-dimensional Pythagorean theorem. All right, well, with our vector function, what's going to happen here, right? So recall that we have our vector function, r of t, and it will be parametrizing our component functions. So x of t, y of t, z of t. And these can then be written, so if as we take the limit, these become infinitesimals, right? So dx, dy, and dz. So what we end up with is the following. But in the limit, let me write it up here. This is exactly how we would have done this in Calc 2, right? So this term this length of pk minus 1, pk, this vector that we drew geometrically. This is actually the length of this value. That's our arc length element that we want to try to find, right? So this is our ds. And this becomes, when we take the square root and we take the limit, these becomes differentials, right? So dx squared plus dy squared plus dz squared. And where do these come from? Well, remember that our function r is smooth, so we can take its derivative. So r dot is equal to x dot of t, y dot of t, z dot of t. All right, and it's differential. So remember, this is dr by dt, right? This is another notation for this. I'll move this up here. So the dot is just kind of in honor of Isaac Newton, the lazy way to write this, right? But if we now want to find the differential, then dr is just going to equal the vector of differentials up here. So this is going to be equal to x dot of t, y dot of t, z dot of t, all times dt. And if we distribute this through, this becomes x dot of t, dt, y dot of t, dt, and then z dot of t, dt. All right, and this can all be written then as dr is equal to the vector of differentials, dx, dy, dz. Now, at this point, why am I doing all this, right? This now, if you compare this with this, what is it, right? The square, to include the whole square root here. This term right here of ds is just the length of this, right? And so what we end up with then is the following. So just by observation here, ds is the length of dr. Okay? Now, we need to plug that into our formula, right? So what we end up with then is that our arc length. This is, remember, this is in the limit. After we've taken the limit, we end up with all this, right? So this is an infinitesimal representation. So the arc length is given by this formula. So L is equal to, we'll just call this S, right? So there's two different ways to think of this. So L is arc length just for L. S, though, is the usual symbol for arc length. So this is going to be the integral from little a to little b. So after we plug into the Riemann sum, we're going to end up with an integral, right? This is going to be the integral then from little a to little b of ds, which is, this is all just notational nonsense here right now, right? This is of the length of the differential, dr, but let's go back and look at where this came from, right? So dr on one hand is equal to this, and on the other hand, it's equal to, at the same time, right, it's equal to this times dt. And so it turns out that the dt can get factored out of the whole square root, and so I'll let you guys work that out on your own. But if you just rewrite in these forms, you rewrite these formulas, then you can factor out the dt from the whole thing. And so probably the best computational way to write our arc length function is going to be, this is going to be equal to the integral from a to b of the length of r dot of t dt. These are all the same, saying the same thing, okay? It's just a matter of how much detail do you want to write these in. So this one is going to be kind of the nicest way to write this for certain reasons as we move forward, but this is totally correct, and so is this as well, right? Now, still, we need to be able to compute this, right? So this is going to be, I'm going to call this S right here. This is our arc length formula, and this is going to be my favorite one for a number of reasons, but it's going to also be useful for us to get these component functions in there sometimes. So another way to write this, if we just get the component functions in there, is that our arc length is equal to the integral from a to b. Remember, these are the values of t, the t values, of the square root of x dot squared of t plus y dot squared of t plus z dot squared of t dt. And that's just writing out the formula for what does it mean to be the length of r dot. All right, so any of these are going to be useful for us. Again, I'm going to probably go with this one. I like these two, this one and this one, for reasons that will be clear very soon. Okay, but now we have these formulas. We've worked them out. By the way, what does it mean, right? So we'll talk about it a little bit more in a few minutes, but the length of r dot is, remember, r dot is the vector that is like the velocity. So the r dot is tangent to the curve at each one of these points, right? And so as we take the limit, these secant vectors approach the tangent vector, right? And so in the limit, that's the direction of the curve, and we have to add up the lengths of those infinitesimal tangent vectors at every point to get the length of the curve itself. So it all makes sense geometrically if you just take a few minutes to think about it and draw some pictures. But what we are concerned with right now is that this is the formula, right? And remember that this formula gives us the length of the curve regardless of the parametrization, as long as the parametrization is smooth, all right? So let's work out the arc length of one of our favorite examples. Let's compute the arc length of one cycle of the helix. So recall that the helix is given by this formula. There are many different formulas, but here's the one that we want to use today. But cosine of t, I, this is the vector function, sine of t, j, and then just t times k. All right. This curve, remember, traces out in three-dimensional space. Its space curve looks something like this. I'm just drawing the axes right now. X, Y, Z. And then I want to work out the length of one cycle. So the one cycle looks like this. So find the length of one cycle. And so this is going to be from the point 1, 0, 0 to the point 1, 0, 2 pi. So we're given all this information. So that's the part that I drew. And remember that this curve just keeps cycling around, right? And becomes a helix. So this point right here, by the way, but just by the way that this is defined, we can see that because this is t, then the t value is going to go from 0 to 2 pi, right? So let me write this here. This corresponds to t equals 0, and this one up here, t equal 2 pi. And that's the portion of the curve that we want to find the length of. So I'm going to give you guys a minute to work this out on your own, and then we'll check back and see how you did. All right, now that you've had a chance to work this out on your own, let's write out the solution together. So I'm going to use this formula. We've already determined that a and b are 0 and 2 pi, right? So there's our a and our b from our integral. We need to work out the length of r dot, though. So that's going to be the bulk of the work here. So the arc length that we want to work out is going to be from 0 to 2 pi, length of r dot of t, dt. So let's write it out. First, we need to write down r. I'm going to write it in our angle bracket notation. So this is cosine t, sine of t, t. And then we need to compute r dot. So r dot is going to just be component-wise derivative. This will be minus sine of t, cosine of t, and then 1. And could then compute the length of this thing, right? So sum of the squares of minus sine of t squared plus cosine squared plus 1 squared. So this is going to be square root of sine squared t plus cosine squared t plus 1. And of course, sine squared t plus cosine squared t, that's a Pythagorean identity for trig functions. So that's just equal to 1, right? And so this gives us the square root of 1 plus 1, which is the square root of 2. Now, this is a function, okay? So this is the length of r dot of t. Function is equal to the constant root 2. So actually it's really nice, right? It's a constant length of the vectors here. So this is what we plug into our integrand, right? We go back up here and we plug in this formula. So we're going to have integral from 0 to 2 pi of the square root of 2 dt. Integral of a constant is just the length of the interval times this number. So we end up with 2 pi times root 2. And there's the arc length of one cycle of the helix. Now, remember that the circumference of a circle, so the circle that if you look from straight above, this looks like a circle, right? The circumference of the circle is just 2 pi. square root of 2 is bigger than 1, right? So this helix stretches out the circumference of the circle as it adds some change in the z component. And the factor right here is just root 2. So that's what we've worked out. So there's an example of the arc length of a helix. All right, so the next thing that we want to talk about is what if we wanted to compute the arc length of a single curve for many different values of ending values. So for example, what if we start with, say, again, our space curve, just some loopy looking thing, C, and we have some starting point here. Let's call it A. All right, that corresponds to R of t0, so some starting t value. And we want to know for any given time t, how far in distance, in arc length, have we traveled along our curve? So maybe this point right here corresponds to t1. Maybe this point right here corresponds to t2. All right, and we want to know can we compute the arc length for any time t? So for any time t. And to do that, we can write down what's called an arc length function. And it's very similar to what we just did. So the arc length function for C, really the arc length function depends on the parameterization, right? So if we go back up, our arc length formula depends on R, depends on the parameterization that we've chosen. So it's the arc length function for C with respect to t, or sorry, with respect to R. It's kind of a weird way to say it, but the arc length function is the key. That's what we're going to define. Starting at R of t0 is given by this formula. So it's going to be S of t. I'm just going to go back up to our formula for arc length and turn this into a function using the fundamental theorem of calculus. All right, we can change this into a function using the fundamental theorem, and here's exactly how we do it. We take the integral starting at our starting t value, t0, going to any value t, so variable t, and then we integrate up our arc length element, but we write it with an integration variable, right? So the t is now up here, and we've got an integration variable, which I'll call u, down here. And so this is our arc length function for any curve that's parameterized by r, right? So it's with respect to the parameterization. T0 is a fixed number, and t up here is allowed to change, right? And so this right here now relates time. It relates time and distance. So this function right here is extremely important. So again, like I said, it relates time of the parameterization to distance of the curve. So parameterization. R to distance on C. All right, so most important thing right here. Let's make sure that this makes sense physically, right? So we've got our function S of t. S is equal to a function, right? S is equal to a function of t. Depends on time. All right. Therefore, and it's defined by an integral. So we should be able to take the derivative of it, right? So what's ds by dt? Well, based on this formula, it's going to be the derivative with respect to t of the integral, right? This integral, and the fundamental theorem of calculus should be ringing in our minds right now, right? Because over here, what happens? Well, this tells us that ds by dt is therefore equal to the derivative of this. So what's it leave behind? Well, just length of r dot of t. All right, and this is not a shock because this is exactly what we worked out before, actually. But this right here says what? The change in distance with respect to time is equal to the length of the velocity vector, or equal to speed, right? So change in distance over change in time, if you think of time and distance as what these variables mean, right? Then this is equal to, remember, this is our function, the length of velocity is equal to speed. And that checks out physically. That makes perfect sense, right? And by the way, this is not a shock because where did this ds come from in the first place? Well, ds is just equal to the length of r dot of t dt. That's what we came up with before, right? Because it's the length of dr. from what we computed when we set this whole thing up. So everything here checks out. It all makes sense, right? It makes physical sense. It makes sense geometrically based on how we worked this out in the first place. And therefore, we can use this function to write our distance in terms of time. All right, so let's go back to our helix then. So this will be number 4, I guess. So I want to do two things. Number one, I want to compute the arc length function for our helix, and then I want to reparametrize the helix with respect to distance instead of time. So this is the main goal here. Reparametrize the helix with respect to arc length. So in other words, I want to get the time out of the situation for our helix. So remember, our helix is given by r of t equals cosine of t, sine of t, then t. And we've already found that the length of r dot, we already worked this out, so we don't have to do it again, right, is square root of 2. So we can write down our arc length function very, very easily, right? So this tells us that, that the arc length function, s of t, starting at, by the way, this starts at t equals 0. Right, so it'll be in our formula, but we did this from t naught equals 0, right? So this will then be from 0 to t of square root of 2 dt, and we can integrate this, right? And this just gives us t square roots of 2, or square root of 2 times t, however you want to write it. But what we get then is this relationship that arc length is equal to square root of 2 times, for this parameterization, time. All right? This is a one-to-one function. This is a linear function, right? And so actually what we can do is solve this one for t. So t is therefore equal to the arc length over the square root of 2. So you can think of this in either direction, right? As long as, once you get this function, as long as it's one-to-one function, it's an invertible function, then you can find the inverse. And you can write this for t. At this point, we can now just make a one-for-one substitution back up here, right? And we can say, all right, so r of t is equal to this, but we can swap out our t for s over root 2, and we can write our vector function of the helix up here as a function of s instead of a function of t. So a function of arc length instead of time. And this then gives us the cosine of s over root 2, second component sine of s over root 2, and then s over root 2 in the third component. And so this is the same helix, all right, the same helix, but it's parametrized in terms of arc length, all right, parametrized in terms of arc length. Okay, so we're going to use this idea of parametrizing with respect to arc length in our next segment as well, or our next item as well. Okay, so the next idea that we want to talk about is something called curvature, and it's exactly what it sounds like, but let's sketch a space curve here and see if we can get a picture of what we're trying to compute. So again, I'll draw some curly Q looking space curve, again given by a vector function or a parametrization r of t, and the idea here is that we want to try to measure how much this curve is curving in space, and that's what the curvature measures. And I think we have an idea of what curving should mean. But here's how we're going to set it up. So at any point on the curve, let's say this one, we can draw the velocity vector. And if our curve is parametrized so that time is increasing in this direction, then our velocity vector, remember, is tangent to the curve. So I'm just going to call this point t here. It's tangent to the curve at this point. All right. And as we move along the curve, say to this point, I'm not going to call that t. Let's call that one t1. All right, t1. Then as we move to another point in the curve, the tangent vector has changed. All right, so this might be t2. And by the way, if we keep going, maybe the tangent vector not only changes its direction, but it also changes possibly its length. Maybe this, at this point, r dot of t3 is much longer than the other two, for example. So the speed is increased, right? What we want to measure is the change in the direction of this curve from one point to another. So the rate of change of the curve from one point to another. However, to make this so that it does not, so that it's a property of the curve and not of the parametrization, we have to take the speed out of the mix. Remember, we're trying to study the properties of the curve itself, the geometric properties of the curve itself, and not of the parametric function r, or the vector function r. So here's what we're going to do. We are going to zoom in, say, on this point. Okay, and at this point, I'll try to draw it in roughly the same orientation. At this point, say this is T. Let's say this is A, okay? At A, we have our velocity vector. Oh, I want to make that a different color, sorry. So we have our velocity vector, r dot at A. And if we go a little bit further away, what we want to do is we want to know how much is the direction of this vector changing with respect to arc length. So there's a couple of things that we have to do, right? So number one, we have to get this in terms of arc length. So we have to reparametrize our curve instead of with respect to A, but with respect to S, right? So the first change that we have to make is to get this in terms of arc length and call this S of A. So we're going to need some starting point. That's very important, but it's very important that we do this right now. The idea is that we want this change to be with respect to a tiny, tiny change in the distance along the curve and not with respect to time, right? So we'll talk more about this in a minute. I'm just going to leave that as it is right now. But the more important thing that we need to deal with right now is that this velocity vector might not have a unit length, right? The length might be changing as well as the direction of this vector. And so instead, what we can do instead is we can swap out our velocity vector for our unit tangent vector at A. Remember, we define the unit tangent vector to be at any point, I'll write it for A, but at any point, it is the velocity vector r dot divided by the length of r dot at that point, right? And remember that our initial assumption at the very beginning of this lecture was that r is smooth, so r dot is not zero, right? So now what we can do is as we move from one point to another, let's get our point, say T2 back in here. So this is T2, and our velocity vector over here looks something like this, right? R dot at T2. We can shrink that one as well, right? And make that a unit vector. Call this T, big T, tangent vector at T2, unit tangent vector. And now as these vectors move along the curve, once we've turned this into the tangent vector field T, then the only thing that's going to change is the direction of these vectors, okay? And the curvature is defined to be the magnitude of this rate of change. So I'm just going to write down the definition now, and then we can do an example and go from there. So here's our definition. The curvature of a space curve. So the curvature of a space curve, C, parametrized by the vector function r equals r of t, all right? So notice this is time, t, is given by, so this is going to be a function now, and this is going to be kappa. That's a Greek letter kappa. When you type it, it looks kind of like this, but this is how you write by hand the Greek letter kappa. This is going to be kappa of s, a function of arc length, is equal to the derivative of the tangent vector field, unit tangent vector field, with respect to that arc length, and then take the magnitude. So this number is going to encapsulate how much the direction of the tangent vector field is changing with respect to tiny changes in arc length, okay? So implicit in this, right, is this issue that I was talking about up here, that if we're given a vector function that is parametrized by t, we need to first reparametrize with respect to arc length before we carry out this computation. Okay, so let me draw a little divider here, and then we'll do an example. So that's very, I have the highlighter. We'll leave it. Okay, so we'll do an example now. What I would like to do is compute the curvature of the plane curve that gives a circle. So compute the curvature of a circle. Curvature of a circle whose radius is a. We'll call it a because r means something different, right? So radius a bigger than 0. All right. And we're going to do it by using this definition. So first of all, a parametrization with respect to t of the circle is one that we're used to, right? It's just a cosine of t and then a sine of t. All right. And so what I'd like you to do now is compute the curvature by doing the following steps. So first, reparametrize with respect to arc length. So with respect to s, so this is arc length. All right, and then 2, compute all these derivatives and put it all together. So compute this kappa of s, but from the definition, right? So take a moment and work that one out, and I'll check back in with you guys in a minute. Okay, so now that you've had a chance to work this one out on your own, let's do it together. The first step is to compute the arc length function so that we can reparametrize this with respect to arc length, right? So here's our function r. It's a cosine t, a sine t. Remember, a is the radius. We're just using a because r means something different, right? We need to take r dot. That's the derivative with respect to t. A is a constant, so this becomes negative a sine of t, positive a cosine of t. And then we need to compute the length of this, right? So the length of r dot of t is related to the arc length function. So the length of this is going to be a squared sine squared t, square everything, right? Plus a squared cosine squared t. The a squared can factor out. So we're left with cosine squared t plus sine squared t. I rearranged a little bit, but that's okay. And then this is the Pythagorean identity. So this is just the square root of a squared, which is the absolute value of a, but a is positive because it's a radius, right? So this is just a. So our speed of our particle, if we think of a particle moving around the circle, is a. It's the same as the radius. And now we need to reparametrize, right? So what is our s? Our s is going to be the integral from 0 to t of length of r dot of u du. So integral from 0 to t of a dt. And this is, of course, just a times t. All right? Again, this is pretty simple, and it's very closely related, very similar to the helix, and we shouldn't be surprised by that because the helix is like a circle that's been extended in the z direction as a spiral, right? And so what we end up with now, though, is that our t parameter that's in our function itself, we're going to have to replace with s over a, s divided by a, right? Just solving for t. And this gives us a parametrization of our function with respect to arc length. So it's going to be a times cosine of s over a, and then a times sine of s over a. All right, and now we're going to compute dr ds. Now, it's very important that you do not use that dot notation when you're dealing with arc length. The dot can be used for any parameter that you could think of as time or like an angle theta or something. But it cannot be used for arc length because we just want to make sure that we keep straight when we take a derivative with respect to arc length as opposed to the parameter, the kind of time-like parameter t. All right, so I'm going to write it this way. And now the derivative, it's very similar to what we just did, except there's a chain rule now. And when we take the derivative with respect to s, we're going to get a 1 over a that comes out. And this one now just becomes negative sine of s over a, and then positive cosine of s over a. All right. So remember, the definition of our tangent vector field, t, was that this was going to be equal to r dot over length of r dot, right? But if we replace this with, I just told you we can't use the dot to mean arc length, but by the chain rule, it's okay. It's going to just be dr by ds over the length of dr by ds. All right, so we still need to do the same computation that we would have done if we were computing t, the tangent vector field capital T with respect to the variable lowercase t. So here's how it goes. We take now the derivative of r with respect to s, which we just did, and then find its length, right? So the length of dr by ds is going to be the sum of the squares of these terms, right? So look what happens. sine squared s over a plus cosine squared s over a, right? This equals just 1. Pythagorean theorem again, right? So this is 1. And it turns out that this is always going to happen, that the length of dr by ds is going to be 1 because the reparametrization puts everything in the right frame, right? So capital T is the derivative dr by ds. But that's not a big deal. So we've got the things that we need here, right? So now we're going to write down our function t, tangent vector field, as a function of arc length. Well, it's going to be exactly this, right? So based on this formula, it's going to be this vector function, right, divided by 1. So this will be negative sine of s over a, and then cosine of s over a. And now we need to take the derivative of this. Remember, the curvature is defined to be dt by ds, the derivative of tangent vector field with respect to arc length. So we take another derivative, right? So dt by ds is going to be a vector function whose components are now, again, chain rule applies. So 1 over a cosine of s over a, negative, stays there. This one we get a negative, and then a 1 over a sine of s over a, and we're almost done, right? The curvature is the magnitude of this, or the length of this. So the curvature, kappa of s, is equal to the magnitude of this vector function, which is then the sum of the squares, square root of the sum of the squares, right? So this is going to be 1 over a squared cosine squared s over a plus, this squared is on the whole thing, but the way I wrote it is a little confusing, right? So let me write it down here, 1 over a squared. Same thing, 1 over a squared sine squared s over a. And then again, Pythagorean theorem, we're going to end up with square root 1 over a squared. That's just going to be 1 over a. All right, so what we've learned then is that the curvature of a circle of radius a is constant, and it's equal to the reciprocal of the radius, right? So this is what we've just proved, actually. So the curvature of a circle in the plane whose radius is a is constant. And not only is it constant, but we can say exactly what it is, right? Kappa constant is equal to 1 over a, 1 over the radius. Okay? So that's an important result that we are going to use very soon. But before we do use it again, let's give some other formulas here. So this is item number 6. Now, the most tedious part of this whole process was reparametrizing with respect to arc length, right? That made this more tedious than probably it seemed like it should have to be. And it turns out that we don't actually have to do this every single time. So other curvature formulas, I'm going to work out the details for one of these, and then I'm going to write down 3 more of them for you for special cases. Those ones you guys should verify on your own and, you know, write out some kind of a proof that those formulas hold. But here's the first formula that I'm going to just give to you, or we're going to work it out together, okay? But remember, I'm going to use the chain rule here. So kappa of s, right, on one hand, let's just write it as kappa. So kappa is equal to, by definition, this is the only definition, by the way, it's dt by ds, okay? But inside of these magnitude bars, we can apply the chain rule. And the chain rule says that we can write this as dt by dt, little t, divided by ds by dt. All right, so this is true by the chain rule. So that's just the chain rule. Okay, now at this point, this upper term, this term on top, that is not a good highlighting color. This term on top, this is just t dot. And this one on the bottom should look familiar. The derivative of arc length is, I'm scrolling. It's right there. It's r dot, length of r dot, right? The speed. It's the speed, the length of r dot of t as a function of t. So these can both be replaced, and this can then be written as the length of t dot. That's t dot, right? The derivative of t with respect to t, capital T with respect to lowercase t, over the length of r dot, and then the magnitude of the whole thing. But this term is a constant function in terms of the magnitude, so this can come out. And so what we end up with is that the curvature as a function of lowercase t, any parameter, is the length of t dot divided by the length of r dot. All right, and so this formula we can always use to go straight from our parametric function to our curvature as a function of t, though. So that makes our curvature a function of t. All right, and so there is our function as a ratio. All right, there are three more forms. By the way, this one works for all, right? For all space curves, for all parametrizations. So this one is for any parametrization. Any parametrization. All right, number two, the second formula that I want to give you, this one works for space curves only. So for space curves meaning in R3. So for space curves only, and again, what I mean by that is our parametrization function maps from R to R3. All right, and here's a formula that you should verify. So I'm going to call this RE. This means recommended exercise. The recommended exercise is that you should work out all of the details to show that if your curve is a three-dimensional space curve, right? If it's a vector function to R3, if it's given by that, then the formula for the curvature can be written in this form. And this is the form. So it's the length of the cross product of R dot with R double dot divided by the length of R dot cubed. Okay, so there's a formula. These are all as functions of t. So notice I have the t here. These are functions of t. Okay, so there's a function for certain scenarios, a curvature formula. Here's another one. What if our space curve is actually a plane curve given by the graph of a function? So for plane curves given by this formula, so something like y equals f of x, all right, then our parametrization can be written in terms of x, right? It can just be written as x comma f of x. And we can obtain, just by, again, using maybe this formula, not worrying about arc length, but just we're using this formula, we obtain the following formula that in this case, the curvature as a function of x is given by the absolute value of the second derivative divided by 1 plus f prime of x squared, square root, that whole thing cubed. So this is an arc length cubed. And that's exactly, by the way, what this is, right? Remember, length of r dot is the arc length element, right? So this is arc length cubed down here. All right, and then there's one more. So again, this is recommended exercise. And just use this formula, plug it in where the x plays the role of the t up here in this, from this formula, and you'll get this directly. Finally, if you have a parametrized plane curve, so not necessarily the graph of a function, right? But for a parametrized plane curve, r equals x of t, y of t. So again, r is a function, vector function of t here. Then what we get, again, you can do the same process, right? Just go through this, work out all the details here. What you end up with then is the following. Again, recommended exercise, you should work out this formula. But kappa of t, in this case, is equal to the absolute value of x dot times y double dot minus x double dot times y dot. Double dot means two derivatives, right? All divided by the square root of x dot squared plus y dot squared, that whole thing cubed. Okay, and again, arc length cubed on the bottom. And then up here you have something related to the second derivative, like concavity, right? So concavity, curvature, it all comes together and hopefully should make some sense. All right, so we have all these formulas at our disposal now, especially after you've taken the time to verify that these last three are indeed valid and true formulas for the curvature. Then we have one definition, only one definition, right? One definition of curvature and four formulas that we can use to compute the curvature. So really altogether there's 5 different ways that we can compute curvature depending on whether we want to use the definition itself or in certain circumstances we can use these kind of special formulas. All right, so let's do another example here, number 7. For this one, I would like you guys to find the curvature. So find the curvature of the parabola, the basic parabola here, y equals x squared, at the point 2, 4. And you can use any one of these formulas. I'll just scroll up this much. Since we were given this in this form, it looks like you should maybe want to use this one, right? So I'm going to give you a minute to work on that, and we'll catch back up in a second. All right, so now that you've had a moment to work on that one, let's work on it. Let's work it out together. This one fits the formula. It is a plane curve, and it's given by a function, right? So this one fits all of the criteria for us to just use this nice formula. 1 plus f prime of x squared cubed. All right, and our function, our y equals f of x. F of x is just x squared, right? And the x is equal to 2 in this scenario, right? So this is what we need to do. We need to take the derivative. Well, f prime of x is equal to 2x. So f prime of 2 is equal to 4, right? Just plug in the x value. And then take another derivative. F double prime of x is 2. So f double prime of 2 is 2. And then plug into here, right? So kappa of 2, kappa at 2, you might say, the curvature at x equals 2 is given by absolute value of 2. I'm just plugging in these values over here, right? Divided by square root 1 plus f prime squared. So 4 squared, and then the whole thing cubed. And so this is just going to be 2 over the square root of 17 cubed. And we'll leave it like that. But there's the curvature of the parabola at this x value equal to 2. X equals 2 at this point. All right, so 2 over the square root of 17 cubed. Okay. The next thing that we want to talk about are some vectors that have a close relationship to our unit tangent vector. So this is item number 8. These are called normal and binormal vectors. So the normal and binormal vectors of a space curve, these help us create what's called a frame, a perfect frame, a frame of reference usually, but it's called a moving frame usually, because as the points move along the curve, the frame is going to change. So let me show you what I mean. We've already talked about at any point, let's call this point P, we know that the unit tangent vector points in the direction of motion, and it's a unit vector, right? So this is a vector that points in the direction of motion. It's a unit vector. Now, from this point, this point now can be thought to create. It can be thought of as the normal vector of a plane, actually, right? So remember how this works. Planes in space, you need a point and you need a direction vector, and that direction vector is normal to or perpendicular to the plane. So this vector is then perpendicular to a plane, and within that plane there are infinitely many choices of vectors that are going to be perpendicular to it, right? And so therefore, we'll have some reference in terms of this plane here. So the idea is if we wanted to say, okay, we've got our tangent vector pointing this way, we want 2 more vectors that we can use to describe the plane or the space of motion, right, of space, so the frame of motion of space with respect to this point as we move along the curve. So we need 2 more vectors to fill out our basis vectors for a 3-dimensional space, right? All right. Well, there's infinitely many choices of vectors that are perpendicular to this t, right, at this point on the plane. But there's one that's very special. So I hope that we remember from the previous lecture that we have this property. So if we have any vector function, so let me write more details here. But if the vector function r is smooth, all right, we know what that means. And if the length of r of t is equal to a constant for all t, right, then remember the result. The result was that the vector itself is perpendicular to its perpendicular to its velocity vector. All right? Well, look what we have in this case, right? The unit tangent vector is if the unit tangent vector is smooth. So this is an if, we should say this, right? So if t is smooth, so this would mean, remember, r dot can't be 0. So if t dot is not 0, so if t dot is not equal to the 0 vector, but it does exist, right? Then what do we know, right? we know that the length of t is equal to 1. T is a unit vector. We built it this way, right? T is a unit vector field. So its length is 1, and therefore, guess what? Its derivative is orthogonal to it, right? So therefore, t is orthogonal to or perpendicular to its derivative, t dot. Okay, so this derivative of t, of the unit vector field t, is going to be a vector that's perpendicular to the unit tangent vector, and tells us something about the curve, actually. All right, so let's write this out. So I'll write it this way. I'll just write this as a definition. So here's our definition. The unit normal vector field, we'll just call it the unit normal vector, capital N at P is given by, so this point P, let's say that this is R of T. Okay, so P equals R of T. This is given by this formula. So N of T is equal to the derivative, T dot of T, divided by its length. We want it to be a unit normal vector. So divided by length of T dot of T. Okay, and then what we have to say here is provided this unit tangent field is smooth. So we've been assuming that our vector function R is smooth. Now we need to assume that T is smooth as well. So if T is smooth, then we get this second vector field called the normal vector field, capital N, defined this way. All right, so this is one way to define it. There's another way, though. So by our same reasoning of the chain rule, right, we can rewrite this. So by the chain rule, so what we just said is completely correct, right? But by the chain rule, N is going to be equal to, instead of this with a dot, we can make it with respect to S, right? So we can write this as dt by ds divided by the length of dt by ds. Just swap out the dots for chain rule again, just like we did before. But look at this. On the bottom, what is that? What is that? That is the curvature, right? That is the curvature. So this is dt by ds, the rate of change of the tangent vector field with respect to arc length, divided by the curvature, kappa of s. And so what we have learned here is the following, is that the derivative of the tangent vector field with respect to arc length is equal to the normal vector field, right, the unit normal vector field, times the curvature function. So the derivative itself is not a unit vector, and we know that, right, because its magnitude is the curvature. And so we get this relationship as well. And so taken together, what all of this tells us then is that we can add into our picture here a vector field that is perpendicular to t, and it turns out it points in the direction that the curve is curving. So it's a unit vector field, points this way. So in the direction that the curve is curving is this vector n. It's given by this formula, t dot divided by the magnitude of t dot. All right, and just a little bit of analysis shows us that it so it's in the direction of the curvature, as we talked about, dt by ds, right? The direction that the curve is curving, but it's related to the curvature as well. It's the dt by ds divided by the curvature function to get the unit normal vector n. All right, now at this point, we have two vectors that fill out 2/3 of our frame of reference, right? And the third one we can get now by just using the right-hand rule, right? So we've got our direction of motion, t. We've got our direction of curvature, n, both unit vectors. If we take the cross product of those two, we're going to get a third vector that obeys the right-hand rule. So the right-hand rule is going to say that these vectors will give back a vector that's perpendicular to both, so still lives in this light green plane, but for which the right-hand rule applies, and it's going to stick out kind of this way, right? So there's B. That's supposed to be going into the screen right there. So remember how this works. You put your fingers of your right hand in the direction of T, you curl your fingers toward N of your right hand, and your thumb sticks in the direction of B. And so this vector right here is going to be called the unit binormal vector. So let me write the definition of that one. So the unit binormal vector field. Again, we don't have to call it a field, but we'll know later in the semester what that means, that word field. The unit vector B at the same point, P equals R of T, so with respect to T, right, is given by, we remember how we built this. We built this as the cross product of T with N, where, remember, the cross product, the order matters, so T has to come first. So it's given by this. This vector B of T is equal to T of T, unit tangent field, crossed with unit normal vector field. So N of T. All right, now we should make sure that this is really, truly a unit vector. So I've called it a unit binormal vector. We know that just from the geometry of it, we know the direction is going to be correct, right? And so now we have this frame at every point, but we need to make sure that this is a unit vector. So let's verify that it's a unit vector. I'll just say that it's unit. So what do we mean? What do we need to do? We need to take the length of B, right? So the length of B is by definition the length of T crossed with N. All right. And remember, there's a formula for the length of a cross product from Calculus 2 that says that this is the product of the length of T times the length of N times the sine of the angle that's made between the two of them, right? Between T and N. And we know all these things. So we built these two vectors so that the length of T is 1 and the length of N is 1. Those are both built that way by dividing out by magnitudes, right? And they were also built so that, using this theorem right here, so that the angle between the two vectors is pi over 2. They're orthogonal, right? And so this becomes sine of pi over 2. And of course, 1 times 1 is 1. Sine of pi over 2 is also 1, right? And so, indeed, the vector field B is a unit vector field just by construction, because we built it as a cross product of two unit vector fields that are orthogonal to one another. Okay? And so this gives us everything we need for what's going to be called our Frenet frame, or moving frame of our space curve. So let's write that down. The vectors T, N, and B form what's called the Frenet frame. It's named after mathematician Frenet. Frenet frame of the space curve C. And because these are unit vectors, then their information encodes the geometry of the space curve itself and does not depend on the parametrization. No matter what parametrization you use, you'll get the same Frenet frame as long as you're working on the same curve. All right, so there's a couple other things that we should say here. So let's call this a new item. But we'll call this one number 8. But I'm going to scroll back up, though, and look at this picture that I drew. So this picture that is the green plane right here. So this green plane is supposed to be the plane that's spanned by the two normal vectors, n and b. That's going to be called the normal plane to the curve. And the curve goes directly through this in an orthogonal fashion, right? So it's like it pierces straight through. If you think of a particle, it passes straight through the plane at a pi over 2 angle, a 90-degree angle in some sense, right? So this is called the normal plane. There's another plane, though. The plane that comes the closest to containing the curve is the one that's spanned by t and n. So t and n together, they form a plane. It's hard to see here, right? But the curve comes really close as possible to living in this plane. It's got the tangent vector in the plane. It's got its curvature vector, the normal vector, in the plane, right? And so it comes really close to living in that plane. And this is called the osculating plane. I'll write this down here, but I'll write down the definition down below. And osculating, this comes from the Latin root of the word to kiss. So it's like the curve kisses the plane, or the plane, you could say, kisses the curve and comes as close as possible to containing it. So maybe it does contain it, right? But maybe not. All right, so here's a couple definitions. So the normal plane of a space curve. By the way, this changes at every point, right? So of a space curve at a point, P equals, again, R of T, is the plane in space, so passing through P, so it shares the point with the plane, so passing through, or with the curve, I should say, through P, and having the tangent vector as its normal vector. So having t of t as its normal vector. So this is normal in the sense of a plane, right? So this is normal in the sense that we talked about at the very beginning when we talked about trying to find vectors that were orthogonal to the tangent vector field t. All right, so that's the normal plane. The osculating plane, all right, this is very important geometrically. It's, again, the plane that's closest to containing the curve. So this is the plane that passes through or contains the point P. I'll say passing through again. That's the way I said it before. And having, this time it has the binormal vector B as its normal vector. So having the binormal vector B of t as its normal vector. All right, and so if I try to sketch this, I'm going to sketch the oscillating, or I'm going to try to sketch the oscillating plane a little bit better for, say, just a portion of a curve right here. So again, this is spanned by, let me get the colors the same. So I think we had green and magenta. So here's our tangent vector. Here's our normal vector, which points in the direction of the curvature. These are both supposed to be unit vectors, right? And then the plane that contains the two of these is going to, it's going to be the plane that comes closest to containing the curve, right? So it comes closest to containing the curve. So I'm going to call this the osculating plane. All right, so again, we've got this vector t, we've got this vector n. All right, now at this point, we've got the plane that comes closest to containing the curve. We've got the tangent vector, so this gives us a direction, right, of the curve in some sense. We have the normal vector that tells us how the curve is curving. And we can encode all of this information, including the plane, all this stuff. We can include all of it by finding an equation if possible. So trying to find an equation of a circle which is tangent to the curve at this point. So my picture, just for the sake of drawing it, is going to both not look like a circle and maybe not look tangent. But the idea is that this is a circle, pretend, all right? It's tangent to the curve at this point. It lives in the osculating plane, and its center lies on the ray determined by the normal vector. All right, so the center of the circle is this. It's even, and I've got even more. Okay, so here's the center of the circle. The radius of this circle is going to be the same as the curvature. So it's going to be 1 over the curvature because, as we found up above, as we proved, right, we want the circle itself to have the same curvature as the curve here. So this circle is going to be tangent to the curve. Remember, this is the curve, this red portion, right? The circle is going to be tangent to the curve. It's going to have the same curvature as the curve, and it's going to have the same osculating plane. It's going to live in the same plane as the osculating plane, and its center is going to be on the normal line. Okay? So this one, we'll call this C1 for center, and the curve itself is C. So let me write down the definition of this osculating plane, and then we will find one for a nice curve. So the osculating circle, I should say. So this circle encodes the curve. It's the best possible encoding of the curve. Maybe not the best possible, right? The curve itself encodes itself, but as far as a simple shape, this circle is going to be very useful for us. So the osculating circle of a space curve, it's going to change from point to point, right? So again, this is all properties of the curve C itself at the point P. And again, this P is equal to R of T. This is going to be the circle that has the following properties. So 1, lies in the osculating plane. There's where its name comes from, right? Well, partially. But lies in the osculating plane. 2, is tangent to the space curve at this point T, right? Or at P, I will say. At R of T it would be. It's tangent to the curve at P. 3, has the same curvature. as C at this point P. And then finally, so it's the same tangent direction. Its center lies on the ray determined by the normal vector, right? So, I mean, that's going to be a consequence of these three. These three are enough to define the circle. Osculating plane, tangent to this, but it's going to be useful in our computations to know this. But so its center lies on the ray. Well, maybe we do need to say this actually, because you could be tangent over here and have the same curvature. So yeah, it's on this side, right? So the center lies on the ray determined by n. All right. So that's the osculating circle right there. That's the definition of it. This thing is extremely useful and important. So let's do an example where we try to find a formula for a plane curve. So for space curves, it becomes a little complicated because you have to find the osculating plane, and then that's going to help you find the formula for the circle, but you're going to have to parameterize the circle as a space curve itself, right? So it's a little bit complicated. It's not too bad, right? We can do it. It's not horrible, but it's a little bit of work. So let's do it for a plane curve now. So here's what I want to do as our last example now. So find the osculating circle for the function, or for the curve, right? Y equals, this one's going to be 2x squared minus x to the fourth at the point 1, 1. So I want to do this at the point 1, 1. Okay, so let's sketch the curve really quickly, and then we can talk about this. But the curve is going to look like it's got what? It's got 3 roots, so it's got symmetric roots here. The roots are going to be 0. There's a double root, and this thing's going to open down. So it's got a double root here. It's opening down. So it's going to do something like this, and it's symmetric. Symmetric. All right. So there's the curve. That's generally what it looks like. This is 0. The other roots are going to be at what? 1 over root 2? Or is it going to be... No, just at root plus or minus root 2, right? Plus or minus root 2. All right, and so 1 is somewhere in between here. So this point 1, 1, somewhere in between here. When you plug in 1, yeah, you do get 1. Okay, so let's just work it out. We need to find a couple of things. By the way, we know because this is a plane curve, the plane that it lives in is its osculating plane, right? So that's going to save us a lot of work. So what do we need to do? Let's first write down the general formula of a circle. So the general formula of any circle is going to be x minus h squared plus y minus k squared equals the radius squared. All right, we need to find the h, the k, and the r. So we need the h, the k, the r. The r is in some sense the easiest one to find because it's going to be 1 over, because of our definition, right? It's going to be 1 over the curvature. So r is going to be 1 over kappa. So the first thing we should do is compute kappa. So let's use remember our formula for kappa. Kappa is for a plane curve, it's the second derivative, absolute value, divided by the square root 1 plus f prime of x squared, quantity cubed. Okay, so we need to compute all this stuff. So our function y is 2x squared minus x to the fourth. Our function y prime, which is going to be f prime, right, is 4x minus 4x cubed. Okay, and then y double prime is 4 minus 12x squared. All right, and then we need to plug in this point. So we need to plug in 1 for these things here, right? So right here, we plug in 1, y prime at 1, or f prime at 1 if you wish. This is going to be 4 minus 4, so that's 0. And for this one, y double prime at 1, this is going to be 4 minus 12, or that's negative 8, right? Okay, so let's see what the curvature is then. We plug in our curvature, plug in all this stuff into here. We get absolute value of negative 8, second derivative, divided by square root of 1 plus, this derivative is 0. 0 squared cubed. And so altogether that curvature is just 8. And so our radius is going to be 1/8, right? Our radius is 1/8. All right. We also learned something else from this, right? We learned if the derivative is 0 at this point, then actually where are we on the curve? Well, then that means that we're right here at this turning point, right? We're at the turning point of our curve. And that means that the tangent line is horizontal. Actually, this curve looks like this, right? So the tangent line is horizontal. Here's the point that we're at, right? If the tangent line is like this, then the normal line is like this. And obviously, just by looking at the curvature is downward. And so the center of our circle has to live somewhere on this normal line, N. Okay? Where does it have to live? Well, it has to live this many units away from the circle so that it's tangent to the circle at that point. So now we know that our circle is going to look something like this, right? So it's going to, I mean, my scale might be completely off here, but the idea, though, is that the circle looks something like that. Its radius is 1/8, so my scale is very much off because the height of this is 1, right? But the radius is 1/8, and we know exactly where this thing goes now, right? Because the x value of this circle is going to be 1. It's tangent, sits directly below the curve at this point, right? And the y value is going to be 1 minus, so that was the height, right? 1 minus the radius. So this is, of course, 7/8. So my work is a little scattered here, but we've got all the pieces that we need now. So now we just write down the formula, right? So the circle, the osculating circle at this point is given by x minus 1 quantity squared plus y minus 7/8 quantity squared, and that's going to equal 1/8 quantity squared. Okay, and so we can leave it like that. But there is the equation of the osculating circle to this curve at this point. I hope you guys enjoyed this lecture. There's a lot of interesting stuff here, and I'll see you in the next one.